Hi. Now, I'm assuming that you've watched the previous video in this series. What I showed you in that video was definite integration. That's integration where we have limits. And towards the end of that video, I just introduced you to one application, and that was finding the area bounded by a curve to the x-axis between x equals a and x equals b. And the formula that we use for any curve of the form y equals f of x was that that area equaled the integral of f of x with respect to x between those limits x equals a to x equals b. Now, I've got an example here which is similar to this particular graph here, so we'd use that formula to work out the area. But in this video, I'm going to take this further. We're going to be looking at the area, for instance, for graphs that are below the x-axis. When we're looking for areas like that, we handle it in a slightly different way, as you'll see. And also, we'll be looking at an example where we're finding the area trapped between a line and a curve. And we'll also do another example where we're looking at an area trapped between two curves. So hopefully you'll stick with this and we'll run through those examples. Now, if you didn't see that last video, just as a brief reminder then, we'll do this example here. So according to the formula then, we've got to work out the area as being the integral of y, which in this case is x squared plus 1, with respect to x, going between the limits x equals minus 1 to x equals 3. And we would write that in like this then, okay? That there's our area. And so if we integrate x squared plus 1 with respect to x in the usual way, we're going to get x cubed over 3 plus x. And then we write those limits on the end of the square brackets here. And if you didn't watch that video on definite integration where we had limits, what we do next is we substitute x equals 3 in first, okay, through here, and then we subtract the result that we get when x is minus 1. So if you do that, substituting those values in, you can see I've put the 3 in first for x, and then we subtract what we get when we put x is minus 1 in. Work this out and you should find it comes to 40 over 3. And being an area, I would encourage you to always write square units. Okay, so that's just to catch up with what we were doing in the previous video. And I've got another example that you might like to try here. We've got this graph, y equals x times all of 1 minus x times x minus 3. And what I'm looking to do is working out this shaded area which I've called A. So you might like to have a go at this, give you a few moments then as usual to pause the video. When you come back, either fast forward to check your solution, otherwise I'm going to take you slowly through it. Okay, welcome back then if you had a go. So let's see how you got on. Well, the first thing we need to do is to find out what these points are on the x-axis. They're going to be our limits in the integration part. Okay, so how do we get those values? Well, it's when y equals 0. And because this is already factorized, if y was to equal 0, then x could equal 0, or 1 minus x would equal 0, or the factor x minus 3 would equal 0. And that would lead to y equaling 0, 1, or 3. So that's where we would start, and I've marked these points in. X equals 1 here, x equals 3, and then it clearly passes through the origin. The next thing we'd need to do is to expand this, okay, because we're going to need it in the integral. So if you were to say multiply the last two brackets out and then finish by multiplying by x, you should find then that you get 4x squared minus x cubed minus 3x. Okay, So when it comes to working out the area now, the area will be the integral of y, which is this expanded expression here, integrated with respect to x between the limits of 1 and 3, as I've got here. Okay? So integrating each of these terms in the usual way, you're going to find you get this result. And then I've put my limits on the end here. Again, we substitute 3 in first, and then we subtract what we get when we put 1 in there for x. And if you substitute those values in, work it all out, you find you get 8/3. And being an area, square units. So if you had a go at that, hope you got it right. Well done if you did. If not, hopefully you can just see your way through that one. Okay, let's take this a little bit further now. I've got another example that I want to look at. I say that. What I've done here though is taken the last question, okay, where we worked out the area of A between x equals 1 and 3. We found that it came out as 8/3 square units. But what happens though if I looked at this bit below the x-axis between 0 and 1? Let's shade it in. I've shaded in here now as B. And it would seem as if we should just simply integrate the equation of the curve. Our limits would be from 0 to 1. Well, let's see what happens if we do that. Okay? If we integrate our expression y equals 4x squared minus x cubed minus 3x with respect to x between 0 and 1, we get the same result as we did here. Okay? Our limits are different, admittedly. We substitute 1 in for x, gives us this result. Take away what we get when we substitute 0 through, so we get 0 there. Work it out, and can you notice we've got minus 5/12. Now you can't have an area which is negative, and that's one of the reasons why I didn't really start off with writing this as the area is the integral from 0 to 1, because I knew that it would turn out to be negative. And this is always the case actually when you have got a portion of a curve below the x-axis, it's always going to turn out negative. So if you do that integral just like that, seeing that in advance it's going to be negative, then we can say that the area of B is 5/12 square units. Just take away that negative sign. If you did want to talk about the area of B and go straight into an integral, then you could have written this, that the area B equals the negative of that integral. So you'd have had a negative sign down here, negative over all of this, and then you'd had a negative 5/12, which would have led to 5/12. Okay, so that's an alternative way that you could set that out. Okay, so we've got our area of B, 5/12 square units, and if we want that total area that is shaded here, A and B, then I clearly have to add these two results together. So if you were to add them together, giving us that total area, it comes to 37/12 square units. So the point about this then is to illustrate what happens when you're looking at sections of a graph that are below the x-axis. Okay, they're going to come out as negative if you just carry out the integral. Now, a common mistake is made here, and I just want to show you what that common mistake is. Hopefully you won't make it, and that is to think of integrating our equation of our curve, y say in general, between say your lower limit here, 0 in this case, up to 3. You mustn't do that when you've got sections of the graph below the x-axis, because if you did, okay, you'll end up with this result here when you substitute 3 in, and you'll take away what you get when you substitute 0 in, okay, because all I'm doing is substituting these values into this equation here, okay, where we've got these three terms. Notice what happens, you end up with 9/4, 9/4. Now the reason why we're getting this answer, 9/4, is because the integral is working out 8/3, this answer, minus 5/12. Okay, if you check that out, 8/3 minus 5/12 comes to 9/4, whereas what we really need to do is 8/3 plus that 5/12. Okay, so hopefully you won't trip up and make that common mistake in future. Okay, so areas under the graph we've got to do as a separate section. Knowing that it's going to come out negative, we need to take care of that by either changing the sign at the end or setting it out like this. Okay, area B, in this case, minus the integral of y with respect to x. Okay, let's move on. So in this next example, give you a chance to have a go at this one where we've got a section of area under the x-axis. So what I want you to do is just try and find this shaded area. Okay, so again, I'll give you a few moments just to pause the video, and when you come back, I'll take you slowly through the solution, or you might want to fast forward to check yours out. Okay, welcome back then if you had a go. So, what have we got to do? Well, the first thing we need to do is establish these points on the x-axis where y is equal to 0. And if we do that, we can set y equal to 0 and our equation becomes 2x minus x squared equals 0. Nice easy equation because we can factorize this by pulling out a common factor of x. And if you do that, you're going to get x times all of 2 minus x equals 0. And that means that this factor x could equal 0 or 2 minus x could equal to 0. So our results for x would be x equals 0 or x equals 2. And could mark those points on the x-axis here. We've got the origin here and we've got this point here as being 2. So the next thing we need to do is work out this shaded area here, going from -1 to 0. So we need to integrate 2x minus x squared between -1 and 0. Let's set that integral up. There it is there. Okay. Integrate each of these two terms in the usual way, and you're going to get 2x squared over 2 minus x cubed over 3 between -1 and 0. Okay. I notice these twos cancel, so that's going to make it simpler to work with. X squared minus x cubed over 3. Put the naught in first then, substitute those limits in, put the naught in and subtract what we get when we put the -1 through there. We're expecting a negative answer. If you don't, you know you've done it wrong, but we do end up with a negative answer, -4/3. Can't have an area then that's negative, so we can therefore say that the area below the x-axis is 4/3 square units. Now we're going to look at the area above the x-axis here between 0 and 2. So we're going to carry out the same integral, this time though between 0 and 2. We know it's x squared minus x cubed over 3, so we just need to substitute our values in. And if you do that, you're going to end up with an answer of 4/3 square units. Just a coincidence, it happens to be the same value as the area below the x-axis. So if we want to get that total area, all we need to do is just add those two values together and we get 8/3 square units. Okay, so nice question there. We're going to move on again. This time we're going to look at a question like this, okay, where we've got an area that's trapped between a curve and a straight line. The curve has equation y equals x squared minus 4x plus 5, I've labelled it C, and the line L has equation y equals 9 minus x. Now you might like to have a go at finding this area R. What I'll do is give you a few moments to pause the video. If it's still causing a problem, what I'm going to do is just explain the method, not showing you the working, but explain the method of how we would take the next steps through the problem. Then you might want to have another go. Okay, so see you in a few moments. So what's the method used in trying to find an area like this then? Well, what I'm going to do is mark in 2 points here where the curve crosses the line, okay, where it intersects. Let's say we call this A and we call this point B. Now, what I'm going to do is drop lines perpendicularly down to the x-axis from A and B respectively. And what I'm then going to do is work out the area of this trapezium here, okay? If I start from the origin, the trapezium goes from O to A, down to B, down onto the x-axis and back across here. But to work out that area of a trapezium, I'm going to need to know this x-coordinate and this x-coordinate. So I can get that by solving simultaneously these two equations, okay? I'm also going to need to know the heights of these two lines for the area of a trapezium, and they're going to be the corresponding y-coordinates at A and B. So I'm going to be working on simultaneous equations there. Work out the area of the trapezium then, and then I'm going to subtract the area that we get beneath the graph, the curve here, to the x-axis, that area in there. So we'll need to integrate the curve between these limits, which we will go on to find, and then I can subtract it, okay, from the trapezium. Just to recap, you can see it with these shapes that I've drawn here. Shape, the area we want here, is equal to the area of the trapezium minus the area under the graph. So if that method now helps you, just give you a few moments then to pause the video and carry on working out this area R. Okay, so see you again in a few moments. So let's start then. We've got our method. We need to find the coordinates at A and B. So we set up our simultaneous equations. I've numbered them 1 and 2 between the curve and the straight line. So in order to solve these, what I'm going to do is substitute equation 1 into equation 2. And if I do that, this is what we get. Now I can rearrange this, make it equal to 0, because I can see we've got a quadratic equation here. I'm going to add x to both sides and subtract 9. So doing that, you end up with x squared minus 3x minus 4 equals 0. We can either factorize this or use the quadratic equation. Well, it does factorize nice and easily to x plus 1 times x minus 4. So each of these factors could be equal to 0, so x could equal minus 1 or 4. So that's what we get there. I can now substitute x equals minus 1 and 4 into the easier of these two equations, although it doesn't matter which one you go into, but obviously 2 is the easier one. So I'm going to substitute those values of x into equation 2. And you can see that when you do 9 minus the 1 here, you end up, I should say 9 minus minus 1, you end up with 10. So A has coordinates minus 1, 10. And when you do 4 into 2, 9 minus 4 gives us that 5. So B has coordinates 4, 5. And that means that we can update our diagram here with those values. We can see that x is minus 1 at A, so this point down here is minus 1. We can see also at B the x-coordinate is 4. At A the y-coordinate is 10, so that means this side here is 10 units long. And for B the y-coordinate is 5, so I can see that this side of the trapezium is 5 units long. And so that means now we're in a position to work out the area of the trapezium. So the area of the trapezium, should be familiar with it. It's the sum of the two parallel sides, 10 plus 5, multiplied by the distance between the parallel sides, so that's going to be a distance of 5 units from -1 to 4, and we divide the result by 2. So it's recapped here. Area of the trapezium is the sum of the parallel sides, 10 add 5, times the distance apart, 5, all divided by 2. And that gives us a total of 75 over 2 square units. Now when we come to work out the area under the curve, okay, this portion here, then I've just got to integrate x squared minus 4x plus 5 with respect to x between the limits -1 and 4. So I've got that in here, and if we integrate each of these three terms, you should find that you get x cubed over 3 minus 4x squared over 2 plus 5x between -1 and 4. Substitute 4 through, subtract what you get when you substitute -1 through, clean it all up, and you end up with 50 over 3 square units. So we need to do this sum. We need to subtract the 50 over 3 from the 75 over 2, the area of the trapezium, and that will give us the area of R. So if I do that, the area of R turns out to be 125 over 6 square units. So quite a long question. Well done if you got this one too, okay, but I do hope that you can see your way through it if it was causing any problems. Right, we've got one more to go, which I think should give you a good selection of examples through this video of the type of things that you're going to get. With this one, you can see that I've got an area here that's shaded, which is trapped between two curved graphs, okay? C1, the red graph, which I've labelled as y equals x squared, and the blue graph, C2, which has equation y equals minus x squared plus x plus 6. So, would you like to have a go at this one? I'll give you a few moments just to have a look, pause the video, and as usual, I'll run through the solution when you come back. Okay, welcome back then if you had a go. So what I need to do with this one is to look at these 2 points where the curves cross one another. We'll call them A and B again, all right, A and B. And what I'm going to be doing now is dropping perpendicular down onto the x-axis there, like so, right? And the method is going to be to work out the x-coordinates. That's all we need to do in this question, unlike the one before where we worked out the y-coordinates of A and B because we were working with the trapezium and we needed to know the heights of these two lines. We don't need that in this example. I just need the x-coordinates of these 2 points, because what I'm going to then go on to do is we'll work out the area below the blue graph to the x-axis trapped between these two lines, and then from that subtract the area below the red graph, okay, down to the x-axis trapped between these two lines. If I subtract one area away from the other, we will get this shaded area. So we need to get the x-coordinates then for A and B. So we do simultaneous equations. So we'll set those equations up. Y equals x squared and y equals minus x squared plus x plus 6. Equations 1 and 2. And I'm going to substitute equation 1 into equation 2, or equate them together. Either way, you're going to end up with this equation here, which when rearranged gives you this quadratic equation equal to 0. And we'll factorize this. If not, you could use the quadratic formula. Factorizing it gives you this, and you put each factor equal to 0, giving us x equals minus 3 over 2, or x equals 2. And you'll see that I've put those values in, x equals minus 3 upon 2 and x equals 2 here. So we just need to find the area below the blue graph, C2, being the integral then of minus x squared plus x plus 6 between those limits. And I've got it here, integrated each term and put my limits on the end. So we'll put those limits in, 2 first, then subtract what we get when we put minus 3 upon 2 in. And we end up with 217 over 12 square units. Now we need the area underneath C1, okay? And we're lucky here, this curve doesn't drop below the x-axis. So I can just integrate x squared between minus 3 over 2 to 2, all right? So if you do that, you're going to get the area below C1. Integrating x squared with respect to x gives us x cubed over 3. So substitute those limits in and you get 8/3 minus 9/8 comes to 91/24 square units, or units squared. And then to get this shaded area here, all we need to do is subtract this area under C1 from the area under C2. Do that and you'll find that you get 343 over 24 square units. Okay, well I hope you're able to get that one correct. If not, again, just able to see how we go about such a problem. So that brings us now to the end anyway of this video. Do check out the links below this video because there's links to exam questions centered on these ideas. Okay, so do give us a like if you found it useful. Hopefully you'll subscribe to my YouTube channel so you get updates when I upload new videos. So thanks for watching. Bye for now.